Linux platform, not the Windows platform. So Windows platform support a lot of things in MS Team but it's recording. Okay, so what we can use actually a lot of profiler. So whatever Tanvis I think so said, I think so. So he said about timing. So we can start timing, start the counter and timer counter and do some work and end timer counter and check the difference. That is one method. Second method is any gprop profiling tool or coverage tool or Valgrind kind of tool. So let me show you some kind of tools here. So how we can check the profiling. So this will be live interactive class. Okay, so in that way you can see. So let me share my screen. So are you able to see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So first thing is one gprop example. So I am increasing by this thing. So here I am taking a very small program, gprop test.c. So are you able to see the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this program have actually main functions. You will look at the main functions. So this have actually two functions. So we are doing 5,000 iterations, and then two functions were running, fun A and fun B. And then we are calling this fun A in fun A, function A. So we are doing something for what again? 10 to the power 5 times. And in fun B, we are doing for 4 into 10 to the power 5 times. And we are calling fun A and fun B, so 5,000 times. So this is a very small program. So for demonstration purpose, I have taken this thing. And if you look at these functions, so main function is calling two functions, fun A and fun B, function A and function B. And function A, both function A and function B is getting called 5,000 times. And function A is doing for 10 to the power 5 times some computations, and function B is doing 4 into 10 to the power 5 times some computations. Okay. So if you look at from the function code point of view, in this case, so function B will take mostly 80% of time, and functions A will take 20% of time. From here also we can see, and the same thing we can get it from actually from a profiler. So let me compile the program. So what compilation will do? So for compilations we go for GCC minus PG, profiling options we are doing and debugging options, and then gprop test.c, and what we are trying to output gprop test. What kind of we are compiling with options minus PG. Okay, this is for profiling. And then once you run this code, so if you look at if you put ls, then gmon.out is there. Let me remove the gmon.out. Okay, so clear. If you do it, there is no gmon.out. So once you run the code, so /gprop test. So it will run the code. It is running the code for some time. Okay. It is taking some time. Okay, now it is executed. And once you put a ls, then if you look at one extra file got created, gmonitor.out. So this is actually at the time of executions, it monitored the executions. Okay, and it put into a file gmon.out. Okay, now what I can do, so I want to see this gmon.out. If you look at the gmon.out, it will not be a readable format. So it will not be a readable format. Okay, so this is very encrypted format on their own way. Okay, but how we can get the profile? So profile to get, you can use gprop, and then /gprop test, whatever the executable, and then if you do, then you will get actually profiling, but we are not able to read the whole screen. So what I am doing, so I am redirecting to a file so that we can read the file. We can read the file. So now this we have the profile.txt, and you can see. So are you able to see my screen?
Yes, sir.
Yes.
Yeah. So here, if you look at function B is taking 77.92, around 80% of time. Function A is taking 23% of time, and both function A and function B called 5,000 times. And this is actually how much time the function itself took. Function B took 4.25 seconds and function A took 1.30 seconds. And this is the cumulative one, function A, and this is including both function A and function B. And if you go down a little bit, you can see how which function called, and this main function called function B and function A 5,000 times. Main function called function B 5,000 times, and main function called function A 5,000. This is actually call graph, we can say, but textual format of representation call graph. So in this way, we can actually see which functions took how much time, which functions get called from which functions, how many time. That information we can get using gprof profiling. So this is a very basic way of doing some profiling. Now, if I want to do something more, suppose SAM code. So I want to see graphically. Okay, SAM code. Graphically, I want to see. So there is another tool called Valgrind. So here also similar kind of code. Okay. So there is a worker one. Okay. There is a worker one. In worker one, we are doing a lot of work. Okay. Worker two are doing very small amount of work. Okay. These are all dummy work. Okay. So worker one, and there is a manager called worker one and worker two. Then project one and project two. And from main we are calling project one and project two, and project one called manager, project two also called managers. So and manager call, this is if you look at first function is for worker one, and first parameter is for worker one, and second parameter is for worker two. So this is 10 to the power 6 worker one and 10 to the power plus 100, and here 1000 plus 10 to the power 6 worker two. Okay. So this is the project one and project two. And what I'm trying to do, which functions call which other functions and how much time, that thing graphically I want to see. We want to see graphically. So how we can do? So here let me show the how this can be done. Run data I am saying. So this is the compilation procedure. So compilation procedure, if you look at for earlier case also we did same thing. So GCC minus PG minus O. So that options were given. GCC minus PG options we give. And now, so instead of gprof, so in that case, we run the program directly. This debug program, it created a file called gmon.out. And in this case, we are running on top of using some tool Valgrind. Okay. And inside the Valgrind tool, we are using another tool called callgrind. And the Valgrind test, we are running on top of Valgrind tool, not directly running. The executable you are running on top of actually Valgrind tool. And Valgrind tool taking the informations, running and generating some another file callgrind.out.pid of the process. Okay. So let's execute all the things one after another. So get run.ss. So let me copy and run all the things one after another. So this is actually compilations using minus PG options. So P for profiling, G for debug. Okay. And then we're trying to run the Valgrind. Valgrind is a tool, value grind. Okay. And from the value grind tool, value grind have actually many tools, and we are using call grind. Okay, so value grind have many soft tools. One is call grind, one is memory grind, other is cache grind. There are many other tools are there. So we are using call grind to see the call graph profile. So this is this Valgrind test. This executable run on top of actually Valgrind. Okay, and then it generated something, so we don't need to care. Then here it generated one file. So what is that file? One new file got generated. Earlier, if you look at earlier 8979 was earlier there, that process ID, but now it generated a new file. Okay, so generated a new file. So now what I need to do? So cache grind and this new generated file. Call grind this new generated file. So I need to see what means decode the things what are there in call grind out 16453. So you can see, are you able to see this thing? My screen. So this
Yes,
is actually
sir.
call
Yes,
graph
sir.
profile, graphical call graph profile. So it start with underscore start. Okay, then we have a main functions. Main functions call two functions, project 2 and project 1. Then both project 2 and project 1 they call manager. Okay, and manager call another two functions, worker 2 and worker 1. And if you look at percentage of time, so here start means basic top node is taking 99%, almost 100%, man also 100%. Then this man also 100%. This is a start node. This is linker start node. Then it come to man and it execute man process. And then from man process, there are two sub functions, project 2 and project 1. And project 1 takes 83% time. Project 2 takes 16% of time. And both project 1 and project 2 call manager functions, which take 99.35 time. And here from manager, we call worker 1 and worker 2. Worker 1 takes 83% and worker 2 takes 14%. We can see the things graphically. Okay, so if you profile your code, so which function is taking how much time and how it is getting executed. If you can see the graphical structure of your code, then you can optimize very nicely. So main motivation of showing this thing is you can use this kind of tool to see the call graph of your program graphically, and what happening you can see graphically.
Excuse me, sir.
Yeah.
Sir, this basically does profiling for functions, right? But most
Yeah,
of the
profiling for functions.
but most of the times when we require analysis of like what is taking the most time in our code, it is inside the main function. Like suppose like not using functions very much.
So look at in this case, 83% of time is taken in worker functions. Okay, so if you optimize the worker functions very nicely, then you will get actually less timing. Your overall time will reduce.
So actually, I mean to say that most of the times we don't use functions that much. Rather, we write code inside the main function in an imperative fashion, and then we want to find out which part of the code takes more time. So can this be done?
No, no. If you look at, let me answer your question also. But if you look at modularity point of view, most of the time we write functional code, have a lot of functions, and which functions take huge amount of, if you can guess. Suppose there are some code which are actually 20,000 lines. Do one put actually 20,000 line in all main functions? Okay, so they will divide the code into different functions, and if you in general standard code writing is actually people write code using different functions. Okay, if you want to put all your code in main function, that is also fine. That another tool you have where which line is getting executed, how many times you can see. Then your problem is also solved. It is fine. Suppose if you know which line is getting executed how many times, we can figure it out. But not in this tool, we'll use another tool. So where that is called G coverage. Okay, GNU coverage, where you will get to know so which line is getting executed how many times. G coverage, that also we'll see. So based on our requirement, we will look at. Okay, so in general, whenever you looked at bigger code, so bigger code we write in actually functional way. And if you can guess the call graph, you can get the call graph, what is the call sequence, and in which way, which function is getting called from which other functions, call graph you get, then you can analyze very nicely. And call graph with timing. So this well-grained call grind, it will give you the graphical picture of call and callee relationship of your program. Okay, so now let me come to your another question who asked, what if I put all my code in main function itself?
Hello,
Okay,
sir.
so yeah, any other question?
So what is 1x and 2x in this graph?
So one time call, two time call, but I'm not sure. So this is one time call and this is two time call. So from manager, it is two time called in the code.
Sir, shouldn't the sum of percentage of time be equal to the time manager is called in the worker 2 and worker 1?
It is it need to be same, but it actually do some kind of what I can say. It try to profile, and based on the profile, it directly reproduce the values. Okay, it should be same, but it is approximately same. We can say, not exactly.
Sir, why don't the percentages sum up to 100?
Sum up to 100. This is actually if you look at these functions. So start. This function supposed to be 100%. Start functions called the main, and this main function again is called the proper main function of your code. Then it divides. It's supposed to be exactly means 100%, but because of this calculation issues, because floating point calculations, so this is some error are there. Some
I
minor
mean to say, in the whole execution time, some part of the time main will be executing, some part of the time worker 1 will execute, some part of the time worker 2 will execute, and so on. So their individual time up should sum up to 100, right? What does 99.35% of
because of the calculation error, there is some 1 or 2% error we are getting.
I mean to say, why is main running 99.35% of the time?
So because of that also it is calculation error.
I'm not talking about the error, sir. I mean to say main should run around 20 or 10% only. Remaining time worker should be running. That's what I meant to ask.
Here also if you look at, this is worker is running around 13.45. It is worker 1 is running 83%. And if you sum it is, you are getting around 99%, 35 something. So here 99.35, here also 99. Because why it is putting 99.35? Because it is doing taking the profiling counter and summing it up. Okay, and it may not exactly map to 100.
So if worker or manager is working, then he means to say that main should not be working at that time.
Yeah.
So why is main taking?
No. This graph shows main function is calling project 2 and project 1 functions one time.
So does that mean it is recording the time for which a main is in the function call stack?
Yeah. Is this clear? Okay, so let me go to another profiling.
So can you provide the command? The commands.
Yeah, we'll provide command. Okay, so there is no issue. We'll provide command. So I'll put this thing in a slide also. Okay. So let me. Another profiling. Let's see. So that's called GCOV. So G coverage examples. So this is the simple code temp.c. So this is, are you able to see the code? It's a very simple straight line code. All the code are available in a main function itself. And for I is equal to 0 to 10, and if total is not less than 45, then we are doing failure or success, something. Okay. So this is very simplistic code, and we want to see, so which line of code is executing how much time. So you want to just see. But this is for one function, but this can be done for bigger code also. Okay. So this, how to compile these things. So how to generate this thing, that I'll put. If you do a main GCOP, this examples I have taken from actually system examples. Okay. So what I am compiling, GCC minus app profile arc and minus app test coverage. That thing were, these are the options we are giving, and compiling the code tmp.c. Then what we are doing? So a dot out. So this it generate a file a dot out with this informations, this debug information, and whenever you run the code, so it will generate something. Okay, it will generate some file. Okay, that is called temp.gcda and temp.gcc number. So these are the temporary file it generates. Okay, for some files for this after running the edit out. Okay, so this is the debug output. So because we have put these things, profile arg and profile coverage, and because of this, this generated two files. Okay, and after this file, we can use gcomp temp.c. Okay, whenever I put command gcomp temp.c, so what it will take? It will take these two as input from the same directory, and it will generate coverage. And it generated a file temp.c.gcomp. And let's see the what is the content of temp.c.gcomp. Are you able to see the screen? You can see this is line number 5.
Yes, sir.
This is executed 11 number of time. Total is equal to total plus I. It is executed 10 times. And if condition is executed 1 times, then this condition executed 1 time, and then return executed 1 time. So which line got executed, how many times it reports. Okay, even if you are putting all of your code in man also, you can see which line is getting executed how many times. Okay, so that is also solved, but for we can use both gprop, gcop, then valgrind to see means how your program is behaving. Okay, in terms of time, which line taking how much time, that we can see all details. This is still, it is very high level. Okay, and suppose you want to see, suppose you know what is the structure of your means processor. Okay, how much cache is there, how much this there, and you want to see the how many cache hit miss is happening. That also we have some tools in Valgrind. We have cache grind also, so we can see which part of our code having a lot of hit and miss. That also you can see, and you can restructure the program based on that. That we'll see later on, not in this class. Okay, and we have seen two functions, and another thing, let me see whether I have or not. This is another code. So this is how you measure the time. So I asked before beginning of the class. So you calculate the time just before doing some. Suppose you want to measure how much time taken by do some work functions. Then t is equal to clock we are doing. This is beginning of your things. Just before beginning we are taking the time. Then after doing the work, we are taking the time. We're taking the time and subtracting the older one and getting the current one. And after that, we are calculating. This gives the clock per second, and after that, in second, we are trying to print this thing. Okay, in second, we are trying to print this thing. And if you compile and run this thing, it will give the how much time it takes in second. So this is wall clock time. So GCC test.c, then this will give you the clock time seconds. So this much clock time it took to execute the your do some work functions. So this do some work, it took that much time. And then some people have told if this same thing can be done with time thing. So time command. Okay, so time command reporting is little bit not good, but using wall clock time is much better. Okay, if you look at e time took 7.05. This is 7.05, and this is user time. This is real time, and user time and real time it add up, and then it will coming to 0.641. Okay, so user time and real time means how much time it spent on user space and what is the time span on kernel space. It mix up both the things and then it generates. So this is the way how we can see how much time our function is taking, our code is taking, which part of the code is taking
Sir.
how much time. Okay, which line is getting
Hello,
how much time. So that can be calculated, seen after executing the program. Yeah, you have any questions you can ask.
Yes, sir. The program that you showed where we calculate the time taken by the program, if any other process is executed in between, like there is context switch happens, in that case we'll get inaccurate time.
Yeah. So this have some interference from the OS. So we don't have control over this. Okay. So this try to take data including that OS interference. Okay, but gprob, whatever gprob also gives, it take overhead. It also included the OS overhead and extra overheads. But number of time it called, so that is accurate because that will not change with actually system conditions, system load conditions.
Yes.
Any other questions? Student side, any other questions?
So sir, when we are talking of system time, we are not taking into consideration the context, so switching bit might happen or if the processor is busy.
This is still, it will give high level one. So if you want to remove the context switch, then in general for taking the profiling, so they generally take out all the loads. So they try to run the code in a very lightly loaded system. So suppose your load of your system is very less than 1 or 2%, then your error will be only less than 1 or 2%. So let me show you what is the load currently in my systems. Okay, so how we can check the load of the system?
Sir, htop.
Uptime, simple uptime is.
Uptime. Okay.
So uptime, simple, very simple uptime. Or top also you can do. So top also you can see, we can say load average. What is the load? So load is here at 2.7. If the load is very less, suppose what I can say 0.2 or 0.3, then whatever are running is actually means almost pre-time kind of thing. That function is off time gives the very good load average is 2.55. We can check if the load is suppose 0.2 or 0.1, then there is no issue. So I have actually quad core machines, so it can go up to load 4. If it is load is more than 4, then you can see a lot of what I can backlog. But if it is less than 2 or 1, then you will not see load. And if it is less than if its load average is 0.2 or 0.3, that means your machine is very lightly loaded. Okay, so what I means in this class I have demonstrated 2-3 tool. So in front of you people. So now let's move towards our regular slides. Okay, so now it is 3:31. Let's move to the regular slides. So this thing, let me put in slides some more. So are you able to see this thing?
Yes, sir.
So
Yes, sir.
how we can measure the performance? So profiling of serial code. So this thing already I have given the demonstrations. Profiling of serial code you can do with manual instrumentations by giving get wall time or clock using clock T. And function and line based profiling using gprob and gcop, that already I have given the demonstrations. Then we can do actually call graph profiling using valgrind and call graph using callgrind, and you can do a memory profiling also using cachegrind. And other profiling thing also we can do using profiling counter. So if you can install OProfiler likewise also in your machines to see the how it is performing. Okay, so this like it is a very good tool. It is from the our one textbook we follow, that is called Hager book. Okay, So they have designed a very good tool, lightweight tool, and you can install in lightweight tool in your any Ubuntu or any Linux machines, and to see the performance of any program. This is much more better up as compared to gprob and gcop, and it gives many other value also. So clearly gcop, gprob, then colgrind, valgrind, then this O profile, lightweight. These are the profiler, or you can see hardware performance counter also.
Excuse me, sir.
Yeah.
So what is this serial code? You mentioned this in last class also. What is this?
Serial code means basically C++.
You mean imperative code, right? Instructions.
Yeah,
okay.
imperative.
Okay.
So manual instrumentations, we can use system status, uptime, top, or VM start, or system monitor or genome system monitor. You can use to see the how your system is getting loaded, all the things. How your suppose you run a program and you see the system monitor, or which processor is getting how much processor is getting used, how much memory is getting used, how much bandwidth is getting used, how much disk bandwidth is getting used. That you can see using system monitor. So suppose you run some program and you can see the system monitor. So and that also means just like task manager. Okay, similar to task manager, we have the system monitor. So let me show the system monitor. So how it looks like in Linux. A system monitor will have this kind of things. So are you able to see the screen? So this is a task manager kind of thing. And if you look at resources, so I have actually 4 CPU. Okay, 4 CPU, and all CPU are utilizing almost likely 50%, and load average around 2 point something. Memory is getting utilized, 4 GB is getting utilized out of 7.7 GB. And this is a network bandwidth, and we can have actually disk bandwidth and all the things also we can take. Suppose you are running some program and instantly, so yeah, if you don't run any other program, suppose instead of GUI, say you switch to actually textual interface and don't run any heavily loaded things, and you want to test for your program, then you will get almost very correct result. Okay, so in this case, I am using this MS Team. Then I am using System Monitor. I am using 3, 4, or 5, 6 what I can say applications parallelly. So that's why your CPU usage is higher. Okay, if you don't run many heavy intensive things, then your CPU usage will be much lesser, and you can test your program how it is behaving. And you can profile. Suppose your program takes 10 minutes to run, and in that 10 minutes, at what time, what is the profile? So first minute, what is the CPU intensity? What is the memory intensity? That you can see also. What is the network intensity? That also you can see. Some profiler. Okay, let's come back to our slides. So this is the time metered out. It gives real clock time, or all clock time, CPU time, and system time that you have already seen. And this is how we can do a manual instrumentation that I have shown this thing. Okay, so take the system clock, do some work, and then take again system clock and take the difference, and finally print the difference. And for doing hotspot analysis, given a program, find out part of the program which takes maximum amount of time, optimizing the hotspot area, reduce the execution time significantly. Suppose a program have actually spent 99% of time in small function or small code. If you optimize that small function or code, optimize that code will result better performance. So you don't need to optimize all the, suppose your program is suppose 2000 line or 10,000 line code, and your program is spending 99% of time in only 10 line of code. And if you optimize the 10 line of code, then you will get huge performance. Why to spend all of your to improve performance in all of your 2000 or 10,000 line of code? You don't require, because other code are simply, it is not taking time for performance. So better to focus on hotspot. Okay, so just like our containment zone. So wherever more number of cases are there, they're focusing on that area. So COVID containment zone kind of thing. So there in program, the engineer, particularly software engineer, we try to focus on the hotspot area. So optimizing the hotspot area reduce the execution time significantly. That is the thumb rule. And whenever you reduce hotspot, then another area, suppose you reduce the time of one hotspot, then it may happen that after reducing, it may create another hotspot. So we need to focus on another hotspot. And once you remove 3-4 hotspots, then your program will perform better. And these are the functional line-based profiling. Already you have seen gprop, and this thing already I have given the demo. And this is all the commands are available in the slides. And this is the same example I took, not other than that. Okay, and same thing we got. And this is the call graph in textual manners. And this coverage also we took the same examples. Okay, and we got this left one is actually it shows the number of time it get executed. And Valgrind also and it is free tool. Valgrind is free tools. So Valgrind have actually call graph, profiler, memory check profiler. Also it give you very good what you can say many more things. From C code one can use API of Valgrinds. Okay, so from C code also you can use some API of Valgrind. Some part of code if you want to test and dynamically if you want to optimize, that also you can do. And this is a program analysis tool useful, bug detector, profiler, and visualizer. And it uses actually dynamic binary analysis tool. So what is dynamic binary analysis tool? So it augments the original code with analysis code and it gives the dynamic informations. And the gprop and gcop. So it's augment the original code, it run the things, and after running it gives the profile profile in gmon.out or some temp.gcda we got files. So it dumped the file and later it analyzed. But here this on top of Valgrind it actually run the code. On top of Valgrind it run the code and it get the profile information. And in this case in Valgrind we can change the cache parameter also. If you run the processor, then you cannot change the cache parameter. But on top of Valgrind, we can change the cache parameter. We can try to run because it run on the top of Valgrind. Just like another virtual platform, it creates and run. This thing already you have seen the same example we took. Okay, and this commands we have used to generate that call graph. Okay, and this kind of call graph we have seen. This thing I have shown by giving the demonstrations. Okay. So now come back to our regular things. So this last part we have already covered, the scalar profiling particularly. So manual estimations, function call, memory profiling, and hardware profile performance counter we have not done, but we can do later. That thing we'll see one more time. And now let's talk with something else. In a program, so if you take simple measure, it have actually larger impact. So particularly many times nowadays, most of the program have actually vector dot product. Are you doing? Have you done any machine learning courses? Hello, students.
We are doing. We
Yes,
have.
sir.
Currently, you are doing, or you have already done machine learning courses?
So for third year, we are doing.
Third year you are doing, or many other people they are already done maybe machine learning courses. In general, if you do, have you heard about this very simple program, matrix multiplication? You have heard about this?
Yes, sir.
Yeah. What in matrix multiplication? What do we do in general? So basic matrix multiplications. So let me show you the what matrix in matrix multiplication what we do. So in general, we have a matrix. Suppose you have a matrix like this. Are you able to see my screen?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Suppose we want to multiply two matrix. Suppose this is A matrix, that this is B matrix, and suppose we want to multiply two matrix and generate another matrix C. So for Cij, for a particular element Cij, resultant matrix C for Cij. So what do we do? So in general, we take ith row and jth column of B, ith row of A and jth column of B means AI ith column and do a dot product or Bj. This is the ith row of A and bth column of J. So ultimately, this is a vector and this is another vector. Okay, so Cij we get by doing a dot product of two vector, Aith row and Bjth column. So we do dot product of Ai and Bj to get Cij. This is the element. So for all elements, for suppose this is n cross n, suppose this matrix is n cross n, then this is also n cross n, then this Cij. So for one element we do one dot product. For whole matrix multiplications, how many dot product it will be? N square dot product. N square dot product. Is this clear? We do n square dot product. And what is the dot product? Dot product means S is equal to summation of, suppose what I am writing is AI Bi. Are you able to see this thing screen? Summation of AI Bi.
Yes, sir.
Yes, sir.
So this is dot product. So A is a vector, element are small ai, and B is a vector, element are small bi. So ultimately what we are trying to do is summation of summation of S is equal to summation of ai into bi. So this is actually dot product. So in matrix multiplication we do dot product, and if you look at any neural network also they have actually two dot product. So this may be summation of xi into wi. So this is weight. Okay, summation of something plus bias and some functions on top of this some functions, and measured times this summation of dot product takes huge amount of time. So in neural network also we have actually vector dot product. Matrix multiplication we have vector dot product. Okay, and all DSP applications, digital signal processing applications, they have dot product. Even convolutions, they have dot product. So vector dot product. So ultimately what happens? If you can speed up the vector dot product, then you can speed up matrix multiplications, you can speed up many DSP applications, you can speed up many image signal processor, ISP, many image processing applications. Okay, image processing domain, matrix multiplication domain, then neural network domain. Ultimately neural network, all CNN, convolutional neural network, deep neural network, they have this huge amount of dot product. Okay, dot product of vector. So if you can speed up this, then many applications can get speed up. Okay. So that's why it is essential to speed up the matrix vector multiplications or vector multiplications, particularly dot product, vector dot product. And SIMD. What is SIMD? Do you know? Do you have any idea of SIMD?
Single instruction, multiple data.
So in most of the processor, we have this kind of instruction, SIMD instructions. Okay, and if you can speed up using SIMD, then most of the time hacking applications get speed up very nicely. SIMD branch, then common subprocessor solution. If you do very simple measure, but it will have a bigger impact on performance. So let's see. So avoid branches, then use of SIMD instructions. These are the three very important things. Elimination of common subexpressions, then avoid branches. This is already common subexpressions already have seen, but we'll see one more example maybe. avoid branches. Code can be summarized and by this is compiler. If you avoid branches, effective use of pipeline for loop code. So if you avoid branches, then you can actually use summarized code. GCC can summarize the thing. What is summarizations? It is a process of converting simple code to other code so that it can utilize the SIMD instructions of the processor. And nowadays, most of the modern processor, they have actually 512 bit of AVX SIMD instructions. Okay, so advanced vector instruction, AVX. AVX means advanced vector instructions. Okay, and most of the ML AI applications use 8-bit operations, can be speed up 512 by 8, 64 time by using SIMD AVX. So if you run your code without AVX and if you run your code with AVX, you will get internally, what I can say, actual running time will be 64 times faster. So if you use AVX. So most of the nowadays ML and AI, they use instead of 32-bit floating point, they use 8-bit floating point or 8-bit numbers they do. So why not to do operation in 8-bit domain? So if you do the things in 8-bit domain, then most of the processors have actually 512-bit AVX, and you can do 64 operations in one go. And most of the JPEG coding, MPEG coding, they use actually AVX instructions. If you download and see the source code of JPEG or MPEG code, then you can see, so they use all AVX coding. And AVX means SIMD means there are many other instructions. Have you heard about SSE, MMX? Hello student, have you heard about MMX instructions? MMX, multimedia extensions, that is called SIMD extensions. So SSE. So these are actually vectorized instructions. So to speed up some particular applications. So this is first thing, whatever the common subexpression relations, another example. So this code, if you look at, so what we are trying to do, value of S, R, X does not change in this loop. So for I is equal to a large number, AI is equal to AI plus S plus R plus sin X, and value of R, value of X, S, all don't change. So why to keep? So you can, because this is commonly executed for all the iterations, you can take out code motion you can do. Okay, so this is also, this will give the huge performance, because for every iterations we are doing sin X operations and two extra addition operations, we can do it just before the loop itself starts. Code motions. This is another thing. This is another examples. So are able to see the code. This top code for I is equal to 0 to n, for j is equal to 0 to n. If I is less than j, s is equal to 1, else s is equal to -1. And then what we are doing? Ci is equal to ci into s into aij into bi we are doing. So here s is dependent upon this predicate if I less than or equal to 0. And if you run this fast code, for what I can say, algorithmic point of view, both are same. But for architecture point of view, is putting the extra this if conditions inside two for loop, nested for loop, it may not give you very good performance. But if you can separate it out, then it can take. What you are separating out, for j is, for j to I you are doing, and in this case s is equal to -1, or putting minus ai minus sign, and for j I to n, for j I to n who are doing plus sign, the same thing. But here this inner for loop is split into two for loop. Inner for loop is split into two for loop. Because it is split into two for loop, now this for loop can take benefit of GCC can summarise this. Summarise means it can convert this instruction to vector instructions. Both inner for loop get converted into vectorized for loop. GCC can do this thing. If we don't do this thing, because of this if conditions, it cannot vectorize the for loop. It cannot vectorize the for loop. Is this clear?
No, sir, could you emphasize more on this? What is vectorization exactly? I did not get that part.
Vectorization means hello. Vectorization means so I'll show you one more slides. So this slide, this is actually vectorization. So this is very interesting slides, and that will clear your doubts. This is vectorization. For I is equal to 0, for a large number, what we are trying to do, AI is equal to AI plus BI into DI over B. Okay. So for every iterations, ith values iterations, it is taking AI, BI and DI, and this can be parallelized very nicely. All iterations in this loop are independent, and GCC can do vectorization and it can run parallelly. Every iterations can be run parallelly. Are you getting my point? Every iterations can run parallelly. So suppose I is equal to 1, I is equal to 2, I is equal to 1 can run parallelly, I is equal to 2 can run parallelly. So parallelly you can run the iterations.
And sir, how is that working exactly?
Parallelly, then it can be vectorized. Vectorized means for whole vector we are doing together.
Sir, I'm not getting the parallel part. How is this being parallelized?
So,
How it can
only
parallel? Yeah.
like only 64 instructions at a time of the loop.
No,
They
in this
can
case, your bit size is actually 8 bit. So each AI is 8 bit, and your APX instructions can do actually 64 operations together. Suppose APX can do 64 operations together. So that means from 0 to 63, it can be done in one cycle. Are you getting a point?
Yes, sir, I got it. It's basically parallelizing in a single instruction, multiple calculations like that.
Yeah.
Okay.
SIMD, single instruction, multiple data. That's why ABX, vectorizations. So
Yes.
that's why it is able to, because it is independent, it can be done. So, but if it is having some if conditions, else conditions, then it is very difficult to do. GCC will not do. So in previous case, even if it is parallelized very nicely, but because of if conditions, it will not do. But in second case, this inner loop, GCC will try to parallelize this thing. You got my point?
Yes, sir. So in a sense, if you have a GPU, so the GCC will try to make it run
Not
on
GPU, not GPU. GPU is different thing. In processor, most of the processing system now AVX instruction, vector instructions, SIMD vector instructions. All Intel processor, all AMD processor, all are vector instructions, except some very old processor, Atom processor or very old Pentium processor, they don't have. But otherwise, most of the processor have AVX instructions. And nowadays, vector instruction size is also 512 bit. Maybe they for newer processor it may be 1024 bit or 2000 bit. Not only 64 operations, you can do actually 128 or 256 operations in one cycle, one go.
And sir, how does GCC exactly recognize this part that these are independent instructions so we can parallelize them?
So for that, there is some small theory is there, but we'll go about very small theory. If you want detail, then I'll give the reference. Okay. So how GCC will do that thing? How this same theory applies to other also for GPU also, but overall process, theoretical process is same. So if you look at, I am showing one more code. Now it is time 3:56, but let me show you one more code. So if you look at this code, so in this code, in ith iterations, AI is getting access, BI is getting access, DA is getting access. You can see this code is very well parallelized. It can be parallelized very nicely. But if I show this code, are you able to see the code? So in this case, what we are accessing in ith iterations, we are accessing AI, BI, BI plus 1, CI and DI. Because in ith iterations, we are accessing BI and BI plus 1, we cannot do parallelisms. In ith iterations, we are trying to access ith and I plus 1 element of some vector bi. This is very difficult to parallelize. So what we need to do in ith iterations, it need to access either ith or I plus 1 of one vector. So not both, or means I minus 1. So it can be only one value, not two values. For ai it is ith, for ci it is ith, di ith, but for pi it is accessing two different value in the ith iterations. So it is not parallelized. If it can access only I plus 1, that's fine, not ith, that is also fine. But because of this dependent loop iterations, it cannot be parallelized. So we need to make it dependent, then only it can parallelize. So if I change this thing to this, hello, the same thing, the same code, we are changing to this code. Suppose n is very large, n is suppose 10,000 or some months 10 to the power 6. Then this code, what we are trying to do? A0 for 0th iterations. So we are taking out, okay. And for last B case, we are taking out from the loop and we are putting at the end. And inside the loop, so ith iteration access ai plus 1, bi plus 1, ci and di. It is not accessing two locations of the same vector. Are you able to see the scenario? This loop is independent loop. It can be parallelized, but previous one is, this one is not parallelized because it is accessing ith and I plus 1 of b in ith iterations, because two things it is getting accessed. But in this case, it is accessing only 1, 1, 1. Okay, so there is a theory behind this, how it can be. This is actually transform one. This is the simple code. It is not parallelized, but if you transform to this code, this can be parallelized very nicely. And which code is parallelized or not, that we can test. Suppose there is a concept called Affine Access. So it is time is 3:59. So we'll see the Affine Access in the next class. Okay, what is Affine Access and how this Affine Access says if GCD of CA. So the Affine Access means AI plus xi plus b. So ax plus b. Affine means linear transform. Okay, so affine means linear transforms. So mx y is equal to mx plus c. Have you heard about this thing? Y is equal to mx plus c, standard index ax plus b form. So same format. This is a linear access or affine access. For any vector access with linear form indexing, then we have a rule. So if GCD CA divides d minus b, then if divides, then it is dependency there. It don't divide, then there is no dependency. So there is a standard theory behind this. That we'll see with examples. In the next class, we'll see this how we can do simulations and other kind of vector optimizations for the code. Is this clear?
Sir, if it is not much effort, can you perhaps share the theory of this? When
Yes, I'll share the theory. So from where I took the reference, that also I'll share.
Okay, thank you.
Okay, so definitely I'll share the theory. Any other questions?
Sir.
Yeah.
Sir, why does two different locations of same vector are dependent on each other? They should be independent, no?
No. Look at, so this code, so and this code. So we are accessing ith and I plus 1 location of b in the ith iterations. So because of this, it is dependent iterations. It cannot be parallelized. But in this case, so we are accessing one location of ai, another location of bi plus 1, ai plus 1, and ci di. So in iterations, we are accessing only one locations. So this can be parallelized very nicely. Whether I or I don't make. We are not accessing multiple locations.
Sir.
Yeah.
Sir, but in this code, the value of b I plus 1 is, I mean, dependent. The S1 statement is dependent on S2.
No, that's fine. But it is statement 1 is dependent on S2. But between iterations, suppose you take I is equal to 0 and I is equal to 2 or I is equal to 1. For iteration 0 and iteration 2 can be, iteration 1 can be done parallelly.
Okay, sir.
So each iteration can be done parallelly. So for previous code, so let me go and see this code. Every iteration can be done parallel. Are you able to see this code?
Yes, sir.
Every iterations can be done in parallel. That is our main concept. In simulations, we looked at from this point. Every iterations, suppose for I is equal to 0 to 512, then we want to do all 512 operations parallelly. Okay, we want to do all 512 iterations parallelly. So that is our main motivations. Simulations means. Is it fine?
Yes, sir.
You got my point, no? Because it is accessing the, in ith iteration, it is accessing only one. It is not accessing others. So that's why it can be parallelized. But S1 is dependent on S2, that's fine. But 0th iterations and 1th iterations can be done parallel. Is fine? Any other question?
Sir, like suppose we write a code and expected that the GCC would in a way do it on a vector operator. So how would we make sure that GCC is indeed doing it as a vector?
No, GCC means this is try to do. If it fails to do, then it will not do.
Okay, so could we know that through some profiler or something?
Yeah. So after first compile the program in GCC similarity options, it try to do. If it is not able to do, then it will say that this part of code I am not able to transform, or it will take more time because it is not able to transform.
Okay.
I need to relook at the code and how to reorganize the code. That is the only way. Okay. And how GCC do that we'll see at very high level. Okay. Any other questions? If no question, then we can stop class. We can stop the class.